So welcome to lecture 34. Um, so in the last class, we were talking about how does the constitutive response of a material look like when you have additional constraint, isn't it? And the kind of constraints that we're talking about was represented by this function phi, and it's a function of right Cauchy Green tensor because it has to be objective, isn't it? So, and then we also saw that the Cauchy stress sigma, for example, could be decomposed as sigma hat, which comes from the constitutive relation, plus a non-reactive term, right? Sorry, a reactive term, which was given by this term n. So it's a reactive term. Okay. And we also found out what's the form of this n. So n turned out to be scalar alpha times f into del phi by del c into f transpose. Okay. Let us see how does this n look like for some specific function phi. For example, if the material is incompressible, so for incompressible material, we had seen earlier this phi of c. So we are saying that for incompressible material, phi c has the form det c minus 1. Okay, and del phi by del c, after doing that calculation, I guess it turned out to be alpha times okay, maybe I'll do it again here, times f. No, del phi by del c was just det c into c inverse transpose, which for incompressible material is simply c inverse because c is symmetric also, no? So this implies n is alpha times f into c inverse, which is f transpose f whole inverse. So that's f inverse into f transpose inverse into f transpose. Okay, you can see that you have alpha times identity coming up, right? So what we have found out is that for incompressible material, sigma has to be of this form. There will be a component which is an active component of stress coming from the derivative of the Helmholtz free energy. But then you have an extra term, which is the reactive term, which does no work. It's in reaction to the constraint present in the material. Okay, so you have this alpha times identity. And it's very interesting that you have this extra term. Um, for example, think of a spherical ball which is incompressible. So we have incompressible spherical ball. And let us uniformly pressurize it from all these sides, from all over its surface, okay? And it's a radial pressure that we are applying. So can someone tell me what kind of deformation will it undergo? Or can you just think about what kind of deformation it's going to go? So you'll notice that, or you perhaps might agree with me that it will actually undergo no deformation because it is incompressible, no? And you are applying radial pressure, the body is spherical. So not just the body has a spherical symmetry, but even the load applied has a spherical symmetry. Therefore, any deformation that has to happen must also have that spherical symmetry. Now, if the final configuration also has to have a spherical symmetry, that means it can only be a sphere of a different radius. But if the radius of the sphere changes, then the volume will also change, right? But because it is incompressible, this means you have this local constraint of det f equal to 1. So locally there is no change in volume, and therefore the total volume will also not change. Okay, so whenever you have incompressible material, it's a highly constrained material where not just the total volume remains constant, but also locally you have volume remaining constant. You can't have somewhere volume shrinking and somewhere volume expanding. It's local det f equal to 1. Anyway, so because it is incompressible, the radius can also not change. Therefore, a sphere remains a sphere of same size. So therefore, it remains a sphere of same size. Okay, this also means no strain develops, isn't it? Because C will be equal to identity. F is identity, therefore C is identity. So what happens then to this active term? Because it has to come from the derivative of the Helmholtz energy with respect to C. Okay, so in that case, this active term will be 0, but this is still something we don't know what it will be. So this then becomes alpha times identity. Now, can you tell me what will this alpha be for this particular case? So you are applying this pressure P from all around. Will there be some stress in the sphere or stress will be 0? There is no strain developing, but still, will there be some stress in the sphere? So Manoj is right, it's minus P times identity, not just minus P, it's minus P times identity. And therefore alpha becomes minus P. Okay, so you're talking about alpha. So yes, alpha is minus P. So you can see that you really need this reactive term to explain or to make it compatible with what happens in physics. In reality, you do have stress even though there is no deformation. And that stress is unknown, which we do not get from constitutive relation because C is identity. So you get it from boundary condition, for example, in this particular case. Okay, so this was one example for incompressible material. Likewise, you can have example of another example of inextensibility along some material direction, say E. Okay, so in that case, what is your phi of C? So first of all, the constraint is that since there is no extension in the direction E, so lambda in that direction is 1, right? Which means longitudinal stretch is 1. And what's the formula for longitudinal stretch? So lambda square, we know it is CE dot E. So phi C becomes CE dot E minus 1. So that's your phi C. Okay, so you should be able to figure out what will N, the reactive component of stress, look like for this particular case. Okay, so N is equal to what here? So think about this. This might come in the exam. So let me, give you a specific example of material models. So you remember earlier I had said to you, if you have an elastic material, you can work with strain energy density function instead of working with Helmholtz free energy density, right? And the relationship was, so the psi is specific energy, it is per unit mass, whereas W is strain energy density, so it is per unit undeformed volume. Okay, and you can get from one to the other. For example, W is simply equal to rho naught times psi. All right, I hope I have not made a mistake here. Yeah. So this you can do if you have an elastic material, for elastic material. So you can work with W instead of psi, where the temperature is constant and you have elastic materials. So one of the models for W, so you know that for isotropic materials, psi depends on I1, I2, I3, right? Invariants of C and theta, of course. So W will also therefore, for isotropic material, W will have those three invariants as argument. Okay. And furthermore, if you have incompressible isotropic material, for incompressible isotropic material, notice that I3, which is determinant of C, will always be equal to 1. So I3 does not change. So therefore, I3 does not show up in the argument of W. So for incompressible isotropic material, W is just a function of I1 and I2, because I3 is not changing, right? So what will then sigma be in this particular case? So if you look at the formula of sigma in terms of derivative of psi with with respect to I1, then that of I1 with respect to C. Remember that your sigma had the form mu times, sorry, it was in terms of B. Let me see if I can pull that out from earlier class. Sigma was 2 rho psi comma 3 I3 times identity plus 2 rho psi comma 1 plus psi comma 2 times I1 into B minus 2 rho psi comma 2 into b square. Now let us suppose we have a very simple material model which is called Neo-Hookean model. Okay, Neo-Hookean. Many of you may have heard about this. So for this model, W, and let us talk of incompressible Neo-Hookean model. Okay, incompressible Neo-Hookean model. So in general, W is a function of all three, but for incompressible Neo-Hookean model, it has this specific form, mu by 2 into I1 minus 3. It only has I1. There is no I2 or I3. I3 is not there because it's incompressible. And for this particular model, I2 is also not present. Okay, so it has only I1. So this is a formula for Neo-Hookean material model. And it is very widely used for soft materials. Okay, widely used for soft materials such as rubber. All right, so if you think of this formula, then what is the active component of sigma? So the one that comes from the constitutive, relation. So as you can see, it has only I1. So that's the middle term where you'll get this term, no? So if W is this, what can you say about psi? So psi is simply W by rho naught, no? So that's mu by 2 rho naught of I1 minus 3. Okay, so what will be then sigma hat? You will have two times rho into psi comma 1. Okay, because it has derivative with only respect to I1, psi comma 1 times b. And when you use this particular form, you have 2 rho mu by 2 rho naught. Okay, and derivative of I1 minus 3 with respect to I1 is simply 1 times b. So what you get is mu times j times b. Okay, and furthermore, j is 1 here, therefore rho is equal to rho naught. Okay, so this is simply mu times b because it's incompressible, no? It's just mu times b. I'll write here rho equal to rho naught for incompressible models. So this is just the active component of stress. This is not all. Because you know that if you have incompressible model, you have that reactive term also, right? So sigma is then going to be that reactive term is proportional to identity, right? And now we'll not write alpha times I, but we'll write it as minus P times I, because we know that it has somewhat the meaning of pressure. It is, in specific cases, it becomes pressure. So this is the formula for stress for incompressible Neo-Hookean model. Okay, the book has several other models, and you can also find on Wikipedia several models. For example, You have Muni-Rivlin, then Ogden model, then you have Blatt-School model, okay, and so many. There are so many material models. And if it is isotropic, they will all be functions of I1, I2, I3. And then you know how to get sigma from them, isn't it? So let's work with, work further with this new Hookean model for the case of uniaxial tension. Let us see what we are getting. Just some analysis. So consider the case of uniaxial stress. Can you think of a practical example where you have uniaxial stress in the body? Anybody? So Minel has this question, won't soft materials be compressible? So most of the soft materials are incompressible. Okay. So their volume, locally their volume is preserved and globally also their volume is preserved for most of the soft materials. There are then cases where the materials are nearly incompressible. That means delta F is very close to 1. But for most of them, it is incompressible. See, nothing in reality is incompressible. It's all approximations. In reality, that's where engineering intuition comes handy. Um, no material will perfectly fit any of the material models, but it will be good enough. There could be error of 3%, 4%, 10%, and it depends on if you are happy with 10% error, and then you can fit with the particular material model. So no material is really incompressible in a perfect sense, but then it is very, very close to incompressible, soft materials. Rubber, for example, it's very close to being incompressible. Just take a rubber in your hand and try to stretch it. When you stretch it, you'll see that its diameter is also shrinking. Well, it happens with all the materials, but in case of rubber, the shrinking will be such that the total volume remains preserved. Okay. Now coming back to this case of uniaxial stress, can you think of an example? Have you done any experiment where the state of stress is uniaxial? So Manoj says buckling of beams, buckling of columns. So yeah, so when you are talking of buckling of columns, to begin with, it's a uniaxial stress case. But once it buckles, it's no more uniaxial stress. But to begin with, originally, when it has not buckled, then yes, it is uniaxial. And I guess many of you may have done this experiment in a strength of materials course. Yes, so Christian is saying this tension test, uniaxial tension test, right? You have this UTM and you are pulling a bar, UTS test. So that's an example of uniaxial stress. Okay. So now what is the state of stress in case of uniaxial stress? If I ask you what will sigma look like? Sigma matrix. So suppose you have this beam and I am pulling it along its axis. Okay. And let us say this is E1 and the transverse directions are E2 and E3. Okay, so you are homogeneously pulling it. In reality, have to clamp the ends of the beam, and wherever you have clamped it, that part does not undergo any deformation. And that's an example. That's a slightly, if you really look at it deeply, you will see that it's a slightly complicated example. It's not the case of uniform deformation, the actual test that you do, because at the close to the points where the beam is clamped and away from those points, the deformations are not similar. Have you noticed this? For example, in the actual testing that you do, the material becomes something like this, because at the ends you're holding the beam, but at the middle there will be more shrinkage, because at the ends you're holding it, you're not allowing it to shrink. Okay, so this is a case of non-uniform deformation. So analyzing it is not so easy. Okay, so I'm thinking of a sort of more imaginary kind of deformation, but which can also be realized experimentally, where you're pulling the beam, but at the same time you're also letting the cross sections at the ends shrink. Okay, so in that case the radius all along will decrease by the same amount, and this will turn out to be the case of uniform deformation. Okay, so for this uniaxial stress, the sigma matrix, how is this going to look like? So you'll only have sigma 1 1, sigma 2 2 will be 0, sigma 3 3 will be 0, and the shear stress components are all 0. Isn't it? Then if you think of deformation gradient, big F, do you guys remember from the quiz question? For the case of uniaxial loading, how will the deformation gradient look like? So if you remember, it's diagonal, all three different, right? Furthermore, don't you think if the beam is isotropic, then the transverse strain in E2 and E3 directions will be same? It will remain circular, right? When you are stretching it or compressing it, a circular beam remains circular. So can't we say that lambda 2 will be equal to lambda 3? Isn't it? Okay. Furthermore, what more can we say? If it's incompressible, so uniquely stress for incompressible material, okay? For incompressible. Then that f has to be equal to 1, no? That's the constraint. That f is equal to 1. So that means product of the diagonal has to be equal to 1, which means lambda 1 into lambda 2 whole square is equal to 1. Okay? Or lambda 2 is then equal to 1 by square root of lambda 1. Okay? Now what about sigma? What will sigma 1 1 be equal to? Supposing that the material is following new Hookean model, okay? Suppose the material follows new Hookean model. Then let us first figure out what is B in this case. So B is equal to FF transpose, right? F into F transpose. And it's being diagonal, F transpose is same as F. And product of diagonals are simply a matrix with product of the diagonal entries. So this is lambda 1 square, lambda 2 square, lambda 3 square, 0, 0, 0, 0, 0, 0, which is equal to lambda 1 square, and lambda 2 square, you see from here, lambda 2 square is equal to 1 by lambda 1. Okay, so it's lambda 1, lambda 1. So that's your B matrix. So what will then be sigma? So sigma matrix from the formula, this is your sigma. So that's minus P times identity plus mu times B. So you have minus P on the diagonal plus mu times B. So plus mu times lambda 1 square plus mu times lambda 1 plus mu times lambda 1. Okay, so this is from the constitutive formula. But it being a uniaxial loading, we know that sigma 22 and sigma 33 are 0, right? But sigma 22 equal to sigma 33 equal to 0. That implies minus P plus mu times lambda 1 is equal to 0, isn't it? Or um, what can you then say here? That P is equal to mu times lambda 1, isn't it? So you see this unknown P, you are able to find it in terms of lambda 1 after using the incompressibility constraint. So with this, your sigma matrix then becomes mu lambda 1 into 1 plus lambda 1. I hope I'm not making any mistake. Okay, I think it's lambda 1 minus 1. And then you have 0 and 0. Okay, or very simply, sigma 1 1 is just mu times lambda 1 into lambda 1 minus 1. Oh, okay, yeah, right. So none of you told me it's 1 by lambda 1, no? It's 1 by lambda 1. I think that is what Krishna Kumar Gupta is saying, no? Lambda 2 square is lambda 1 inverse, yes, 1 by lambda 1. So sigma then becomes, here you have mu by lambda 1. And so from here you have mu by lambda 1 equal to 0, or P is equal to mu by lambda 1. So finally you can come back here and P is mu by lambda 1. So what you get is different, of course. So it's mu lambda 1 square minus mu by lambda 1. So this is same as mu lambda 1 square into 1 minus or I should just say mu into lambda 1 square minus lambda 1 inverse. Is that okay? Similarly, you can think of simple shear. How does it look like when you have simple shear? So in the book, they have also talked about the case of simple shear. You can look at that. So simple shear response for incompressible new Hookean model. So if I ask you similar questions in the exam, you should be able to do it. So this is the response for uniaxial loading of a new Hookean model. So how does sigma 11 change as you change lambda 1? Okay, any questions so far? So like I said, there are several material models discussed in the book also. Fung model, then you have Gent model, and they all have interesting applications. And if I give you any one of the models in the exam, you should be able to find out what will be the sigma for such a model. And also, if I say, okay, a body is undergoing, let us say, uniaxial loading or simple shear, then what will be the response of the material? So you should be able to answer that in the exam. So I'll take another class tomorrow that will be on linearized thermoelasticity, and that will be the last topic. And that's in chapter 8.9. So we have till now looked at the nonlinear equations of thermoelasticity: linear momentum balance, angular momentum balance, then energy equation, entropy inequality, and then you also look at this constitutive model. This, for example, this new Hookean model. This one. So it's a nonlinear material model because the invariant I1, I2, I3, for example, they are nonlinear in displacement. It's a function of C, right? And C is F transpose F, which has identity plus grad U transpose plus grad U transpose into grad U. So C is not linear in strain. It has also a quadratic term. And I1, I2, I3 are coming from the invariants of C. So therefore, they're all called non-linear material models. Okay. So when we talk of linearized thermoelasticity, not just the equations are linear, we have to look at linear equation, but also the models, the constitutive models also have to be linear. So we'll talk about that in tomorrow's class. And this is going to come from the nonlinear equation itself. So you have to linearize the equations that we have already derived. So the equations that we have derived are more general. It holds for large deformation also. But for the cases where deformations are very small, or where you can say that gradient of displacement is much, much less than 1, for example, of the order of 0.01, 1%, 2%, if the gradient of displacement is of that order, then you can work with linearized theory of thermoelasticity, which is simpler than the nonlinear equations of thermoelasticity. But it's not a new equation, it is derivable from the nonlinear equations. You simply have to get rid of the nonlinear term. Okay, so that is something we'll do tomorrow. So look at this response, for example. sigma 1 1 equal to mu times lambda 1 square minus 1 by lambda 1. So it's a nonlinear response. It's a non-linear response. So if you draw the graph of sigma 1 1 versus lambda 1, you won't get a straight line. Okay? So this is not correct. You'll have a curved line, basically. So therefore, what you have here is a nonlinear response. And of course, you can linearize this. You can think of linearizing this in lambda 1 by neglecting the higher order terms in lambda 1. Okay, so let's talk about that tomorrow.
Sir, in F matrix, the lambda 2 equal to lambda 3. Can you explain that?
Yeah, that's from physics. See, we have this circular beam and you are having uniaxial loading. Then don't you think that the deformation in 2 direction will be same as deformation in the 3 direction?
Yes,
Because
sir,
it's
I
in,
think that. But in previous, when uniform deformation we were doing, you didn't take anywhere that lambda 2 equal to lambda 3. That's why I'm asking.
right, so that was a general uniform deformation. This
Okay.
is a specific case for uniaxial loading of a circular beam, isotropic circular beam. In that case, the transverse deformations are same, but in general, it is not the same.
Okay, sir.
Yeah.
And the p value, it is pressure or some general constant.
P value, where, which P?
It's
You
in
mean here,
sigma.
the P that we found out.
Yes, sir.
So yeah, this is not a pressure anymore. You see, it's first of all, it's a solid body, right? And sigma, have a look at this sigma. What is the form of sigma? This is the form for sigma. So it's not really like pressure.
So it
It's
is a
you can
general
think for
constant
it
that we have to find.
it's more like an unknown
Okay.
here.
But
So can we think this?
when we were deriving at incompressible spherical ball, then we have considered it pressure or some general constant only.
Yeah, so that was a very specific case for a spherical ball where the alpha turned out to be equal to the pressure that you're applying. But that won't be always.
Okay.
Yes.
Sir, this P, can we not think in this case of uniaxial stress as like some uniaxial pressure is getting applied over the area?
No, because that is sigma 1 1. So sigma 1 1 is what
That
you're
is the response. That is like internal response, but something external must apply to.
which has to be equal to what you're applying externally. See, because this is a beam, so internal response here will be same as what you're applying externally at the ends. So that's your sigma 1 1.
Okay. So now P, we have got a restriction, like P has a particular form here for this particular case. So
Correct.
I think that is also intuitive that load we cannot control like this. No? If we think in terms of load, then we cannot tell it as like mu by lambda 1. We can apply any arbitrary load. So P is here not representing the load exactly.
Yes, P is not the load, of course.
Okay.
Sir, why can't we relate lambda 2 and lambda 3 with lambda 1 by using Poisson's ratio?
See, here, of course, from here you can derive what will be Poisson's ratio. But this is see the concept of Poisson's ratio, which is whenever you have this uniaxial loading, the ratio of transverse strain to longitudinal strain, right? That is what we call as Poisson's ratio. So that is something you can also derive here. So what will be, for example, minus of, so let me do that here. So it's a very good question. So Poisson's ratio, to be very, very rigorous, it's when you are doing, so you have to first do uniaxial loading problem, okay? And the Poisson's ratio is then negative of transverse normal strain divided by longitudinal normal strain, isn't it? Or I should say the strain in the direction of applied loading. In case of beam, it is longitudinal normal strain, and then you have transverse normal strain. But this number also, for the case of non-linear material model, this thing will keep on changing as you apply the deformation. Just have a look at in this particular case, what will be, so this is then minus of lambda 2 minus 1 divided by lambda 1 minus 1, isn't it? And what's lambda 2? So lambda 2 is, we already have it in terms of lambda 1, right? So lambda 2 is 1 by square root of lambda 1. Okay. So that's minus 1 by square root of lambda 1 minus 1 divided by lambda 1 minus 1. Okay. As you are stretching the material, this ratio does not remain fixed. It is changing. It's a function of lambda 1, right? So the Poisson's ratio is changing as you are stretching the material. But the Poisson's ratio that we have been talking about, it is for the linearized theory of elasticity, where it's a single constant. So maybe here also, if you find it, what is this ratio when lambda 1 is very, very close to 1? What is this equal to? That will give you kind of Poisson's ratio in the linearized theory. Okay, so let us try to do that and see if we get something. So supposing that lambda 1 is positive, then what can we say here? Yeah, so this is then minus 1 minus square root of lambda 1 divided by square root of lambda 1 into square root of lambda 1 plus 1 into square root of lambda 1 minus 1. Can we say this? See, these two together is lambda 1 minus 1. That's in the denominator. So this is then same as 1 by square root of lambda 1 into 1 plus square root of lambda 1. So this holds for every lambda 1. Now we have to set lambda 1 equal to 1 in this, because I want to look at that ratio when lambda 1 is very, very close to 1. So when you do that, what are you getting? Can you see? So it's becoming equal to 1/2, isn't it? For lambda 1 close to 1. And you must have learned that for incompressible material, the Poisson's ratio is 1/2, right? And that is
Yes,
why
sir.
you are getting this 1/2 here. But in general, for a large deformation case, Poisson's ratio does not remain fixed. As you can see here, it's a function of lambda 1.
Sir, while assuming this, like while cancelling this 1 minus root over lambda 1,
Yes,
did we not assume that lambda 1 cannot be equal to 1 because denominator will be undefined, will be
right.
0?
So in that case, you have to apply L hospital rule and then get it, and you'll
Okay.
get the same thing.
Okay, so we are using the limit actually here.
Yes, exactly.
Okay, sir.
Yeah.
Sir, in continuation with this question only, like when we
Yes.
analyze for finite deformation problems, so there
Yes.
mu like our Poisson's ratio keeps on changing, but when
Yes.
we model the material, even non-linear material models,
Yes.
we keep the Poisson's ratio as something like constant value only, like we do not change it. So whether the variation is not much, that's why we keep it same, or like it will not have any effect. And because in the softwares and all, when we do even geometric nonlinearity cases and all, we keep mu as some particular constant only for that material.
Right. So you see, it all depends on what model you are using. If you talk of reality, then obviously Poisson's ratio is changing. But if the change is not significant, then you can assume that it's constant. So that's the
Okay.
thing. And there are two kinds of nonlinearity. There is one is geometric nonlinearity, and the other is material nonlinearity. So in
Yes.
case of geometric nonlinearity, you work with large deformation strain, which is your Green Lagrange strain tensor, for example, big E.
Correct.
That's half of C minus identity. So if you write it in terms of displacement, it becomes half of grad U plus grad U transpose plus grad U transpose into grad U. So this is the nonlinear term. So if you are also keeping this, that means you are having geometric nonlinearity in the model, which is more accurate thing to do when you have large deformation. But then there is also something called material nonlinearity. So in case of material nonlinearity, the energy will be quadratic in strain, big E, or you can say that stress versus strain response will be linear. Then you have material linearity. If the stress versus strain response is nonlinear, then we say it is materially nonlinear model. So there are several models. And in case of materially linear model, you can say that the properties are not changing. For example, Young's modulus or Poisson's ratio, they remain fixed. In case of materially linear model. But if it's a materially non-linear model, then the model will allow for the properties to change as the deformation is happening, the Young's modulus or Poisson's ratio. But to be more rigorous, I must say these Young's modulus and Poisson's ratio, they are always defined for small deformation case. So when you have large deformation, no, there is nothing like concept of Young's modulus or Poisson's ratio. Young's modulus and Poisson's ratio are only for, they are only defined for small deformation. So what I'll tell you is that what I mean to say is that Poisson's ratio nu is, for example, minus epsilon 22 by epsilon 11 when epsilon 11 is very close to 0. Similarly, the Young's modulus E, that's sigma 11 by epsilon 11 when epsilon 11 is very close to 0. And this you have to get from uniaxial loading. If you do biaxial loading and then try to get this ratio, you'll get different modulus. You must do uniaxial loading and then get this ratio and evaluate it at epsilon 11 equal to 0. That will give you Young's modulus. So this is the exact definition of Young's modulus. And when there's nothing like Young's modulus changing as the deformation is changing, because Young's modulus is defined at epsilon 11 equal to 0. Okay, but many people just say that, okay, I'm keeping the property fixed, Young's modulus is not changing, but it's not like that.
Understood.
Yeah.
Sir, one doubt here.
Yes.
So like the stress strain curve which we used to draw,
Hmm.
after the linear part, like we get
Yes,
a non-linear relationship between
correct,
stress and strain. So in
correct.
that reason, we cannot apply these two values, mu and e, because like these are defined for a small deformation.
Right. Yes, yes.
Okay, sir. So sir, for that, do we have any other like theories? Uh,
Yeah, like I said, no. So whenever you have, so if you draw this sigma 111 versus epsilon 11, and it's initially it is linear, and then it becomes non-linear. So this entire thing, you some what you do is you do experiment and you find that okay, this is what the graph is. Then you try to fit it with one of the existing material models, for example, New Hookean or Muni-Rivlin or Blatsko or Ogden material model. So this entire graph fits, or at least gets fit closely with one of the models. Or you can come up with your own model by fitting it with with some optimization tool. You can come up with a formula. And that you will say is your new material model.
okay, sir.
Yes.